So, we're going to continue our discussion of conservation of momentum in this second part of linear momentum and collisions. I apologize for any tapping sounds you might hear in the background, but I'm recording this in an upstairs room and it's raining outside quite heavily. So, by conservation of momentum, what we're really discussing is what happens when bodies interact. Momentum is always conserved in any interaction, in any collision. So, what does that mean? It means the total momentum before a collision is the total momentum applied to the system after the collision. The masses, in the cases we are looking at, will stay the same. This means that velocity is the key quantity that is not the same for each body after the collision. When we're talking about collisions, we can divide them into two simple groups. Inelastic collisions, where the total kinetic energy of the system is not constant, though the momentum is, or elastic collisions, where the total kinetic energy is constant and the momentum is constant. I tend to remember this more, that in an inelastic collision, the two objects stay and move together as one after the collision. So, in an inelastic collision, if the Earth is moving through space and a meteorite comes along and hits it, the mass of the meteor is added to the mass of the Earth, and then the Earth really continues pretty much unaffected in its original velocity. Take a NASCAR situation where people have to turn left and can't manage that. In this particular case, these cars have crashed together, and what we would have is before the collision, we would have multiple masses with their own velocities. After the collision, we have one large mass with one common velocity. So, for the inelastic collisional case, if we are to apply conservation of momentum, then what we can say is before the collision, we have two masses with two discrete velocities, m1 v1i and m2 v2i. This is going to be equal, after the collision, to two objects being stuck together essentially, not adhered, but moving together as one. So we'll have after the collision, Pf will be m1 plus m2 times some common final velocity, giving us an equation with essentially three terms. That means if we wanted to find the final post-collisional velocity of this system, we could rearrange and find it by rearranging for v to say m1 v1i plus m2 v2i, the initial momentum, divided by the addition of the two masses. So what does this mean for a calculation? Let's look at a basic case. So here we have two astronauts. Astronaut 1, who has a mass of 160 kilograms and a velocity of 10 meters per second. He's going to fly into astronaut 2, who's of equal mass, 160 kilograms, and his velocity is 0. Astronaut 1 is going to hold on to astronaut 2 and follow them, and following the collision is going to move with him. Two questions. What is the initial momentum of astronaut 1 at t equals 0, so at ti essentially? What is the final post-collision velocity of the two astronauts? So astronaut 1 is going to hit astronaut 2, and the only equation we're going to apply is P equals mv. So this is a classic inelastic collision situation. So what is the initial momentum of astronaut 1 at t equals 0? Well, astronaut 1 has a mass of 160 kilograms and an initial velocity of 10 meters per second. Astronaut 2 has no momentum because if we multiply his 160 kilograms by 0 meters per second, we're going to get 0 back. Consequently, P1 or Pi is going to be M1, the mass of the moving astronaut, 160 kilograms, times 10 meters per second, giving us 1600 kilogram meters per second. The final post-collision velocity of the two astronauts, however, is going to be a little different. So astronaut 1 is bringing all of this momentum to the party. Astronaut 2 has no momentum. That means the final post-collision velocity is going to be the two masses added together times some final velocity. If we rearrange, we can then say Vf is then going to be our 1600 kilogram meters per second from here, divided by 320 kilograms. That'll give us 5 meters per second. In other words, we could have figured this out much more simply, that the initial velocity of the astronaut was 10 meters per second. We doubled the mass. We took the mass from 160 to 320 kilograms. That would have the effect here of halving the velocity. Sometimes in the slides I put these in to help the PDFs along. There's no animations here. This is just two objects colliding. In this particular case, they've both got a velocity towards each other. Their velocities could also be in the same direction. This was more of an arbitrary choice. But here we have two discrete objects with their initial discrete velocities, and afterwards we have their masses added together and some new final velocity. So let's take a look at another problem. In this case, we have a car, mass of 1,000 kilograms, traveling at 27 meters per second, and it's running head-on into a truck of mass 8,600 kilograms, and the truck's moving at 10 meters per second. What's going to be the velocity of the car-truck wreckage after this impact? Remember, in this particular case, the car is moving right to left, the truck is moving left to right. That will apply a negative value to the velocity of the car. So, what is the velocity of the car-truck wreckage after the impact? So you can see in the left-hand diagram here, just very simply, this is the truck, the car, and the velocities are added together. So the total momentum, remember, is conserved in the collision every time. So that's one thing you can write at the beginning of every problem, is that Pi is equal to Pf. This means our pre-collision momentum is going to be the mass of the car, which was 1,050 kilograms, the velocity of the car of 27 meters per second. So the initial momentum of the car is 1,050 times negative 27. Remember, the car was traveling right to left, giving us a total momentum for the car of negative 28,350 kilogram meters per second. The truck will have its own momentum, which is going to be m truck times velocity of truck, which is going to be 8,600 times 20 meters per second. That's going to give us 172,000 kilogram meters per second. Now, this is where we have to invoke our conservation of momentum. We calculated the total momentum at the beginning, and we calculated the total momentum at the end. In other words, Pi and Pf. Now, Phi final is going to equal to the total mass times the final velocity. So what I'm saying is, our final momentum in an inelastic case is going to be the two masses added together multiplied by the final velocity. That's going to give us 9,650 kilograms multiplied by Vf. So what we have is the total momentum is going to be the initial momentum of the car plus the initial momentum of the truck. So here we have our equation. Here's our initial case, total case. This is going to wind up being 143,650 kilogram meters per second. P total, F, the final momentum, is equal to the total mass multiplied by the final velocity. So what we can say is the initial momentum has to be equal to the final momentum. So this is the initial momentum we calculated, adding mv for the car and mv for the truck, and that's equal to the mass of the truck and the car combined times the final velocity. Rearranging for Vf gives us the 143,650 kilogram meters per second divided by the 9,650 kilograms. Of course, that will cancel these units and we'll end up with an answer of about 15 meters per second. So, not only can we look at collisions in terms of momenta, we could also look at them in terms of kinetic energy. And here's a famous example that apparently before Netflix existed, this was the thing you'd do for entertainment, was a guy called William Crush in Texas decided to take a couple of obsolete steam locomotives and smash them into one another for fun and charge people to see this particular spectacle. So what he did was take these two steam locomotives, each weighing 1.2 times 10 to the 6 newtons, and stage a train crash. He placed them at opposite ends of the track and then fired them up and let them go, and their throttles were jammed open and accelerated at 0.26 meters per second and smashed head on into one another. He did pretty well out of this because he'd sold tickets to 30,000 spectators, and if you want to see a video of the crash, here it is. You can hit this link and you can have a look at that. Here's the result. The impact actually injured hundreds and hundreds of people, but only killed about 3, which was actually quite fortunate considering what we were about to discuss. So if we assume that each locomotive was under a constant acceleration, what would be the total kinetic energy of the two locomotives as they smashed into one another? We've got the weight of the locomotives, 1.2 million newtons. We've got the displacement of 6.4 kilometers, and we've got an acceleration of 0.26 meters per second. So here's a bit of a simulation. Here's our trains, either end, here's our accelerations, and here's our distance. And these trains are going to come together and smash into one another, and then they're going to explode, of course, and the resulting injuries are something we're not responsible for. We're just doing a scientific calculation. So let's take a look at this. Let's analyze this situation in a real sense. We've got the weight, we've got the acceleration, and we've got a displacement. We have to go back to kinematics here. We have to use v squared equals vi squared plus 2as. Here's a separation of the locomotives. Here's a. Here's the initial velocities. The separation is going to wind up being half of that 6.4. If the track is 6.4 kilometers long and we assume they're both moving at the same rate, then they should meet exactly halfway. So we're going to say that the separation was 3.2 kilometers. So 3.2 times 10 to the 3 meters. We know the acceleration is 0.26. We're assuming they started from rest at the ends of their track. So this is going to be 2 by 0.26 by 3.2 times 10 to the 3. So our velocity, if we take this and root it, will wind up being about 41 meters per second. So the mass of each locomotive is something we still have to calculate. We had that given as a force, inconveniently, in this question. So the mass will be force over acceleration, where acceleration here is g, 9.8 meters per second. 1.2 million divided by 9.8 gives us a mass for our locomotives of 1.2 times 10 to the 5 kilograms. Now we can take that mass and we can calculate the kinetic energy. So half that mass times v squared is going to give us 6100 by 1664. That's going to give us about 10 million joules of energy. Just for reference, the average hand grenade energy release is about 4,000 joules of energy. So when Mr. Crush decided to sell tickets for people to come and stand next to the track, what he was actually doing to them was setting off about 2,000 hand grenades, which was incredibly nice of him. It's not to be advised to crash two trains together for entertainment. Just go and watch Game of Thrones or something. Our next section really deals now with the other family of collisions, which is elastic collisions. And this covers things such as pool balls, bashing together. If you imagine pool balls, unless you're very, very good at this game, which I am not, I tend to take out the lights, the balls will collide and should come apart, starting with two balls at the beginning and finishing with two balls at the end of your interaction. This is what we mean by elastic collisions. You have two discrete objects before the collision and you have two discrete objects following the collision. This is a sort of typical assumption that is made when we're dealing with air molecules in something like gas laws. We assume that no interactions between the walls of an oven are made, even though that's an untrue scenario. It's a very nice generalization that makes our calculations work. So air molecules hitting a wall at standard temperatures and pressures essentially are treated as elastic collisions that are preserving their momenta. What we're saying about an elastic collision is, unlike an inelastic collision where the objects move together after their impact, the two objects come together, hit one another, and then essentially go away as two discrete masses with their own velocities. So these two cars came together in an impact, M1v1, M2v2, and bounced off and had an M1 V1 final and an M2 V2 final. So our equations end up with four terms in them. Here's our equation in momenta, M1 V1I, M2 V2I, M1 V1F, M2 V2F. And similarly, if we were to express this in kinetic energy form, which is really momenta with halves and squareds included in them, then we would see a very similar relationship. So, for an elastic collision, our interaction is such that two objects come together in an impact, and then afterwards we still have two discrete objects after the impact. In reality, an elastic collision is never perfect. What really happens is if you hit pool balls together, for instance, there's a clonking sound, there's noise, there's deformation of material, there's friction with the surface. We're not really going to worry about those things. Once again, those are things we could find and we could add to our calculation and make it so complicated that we'd be here till next year trying to figure it out. Consequently, we often assume elastic collisions are perfect and simplify it and just say momentum is perfectly conserved in these cases, and that M1v1i plus M2v2i is equal to M1v1f plus M2v2f. So those are our two families of collisions, elastic and inelastic. What we're going to do in the third lecture in this series is take our momenta and our kinetic energy and look at these in terms of two-dimensional systems.